My name is Samuel, and I'm here to present joint work with Mohit, Stefano, and Luc, as well as Adam, Andrea, and Patrick on learning constraints and combinatorial optimization problems. Now, everybody in AI uses constraints, but there's few people who actually learn them from data. And I'm talking about inductive learning, not speed-up learning, such as clause learning. And I want to review some key techniques and recent results. A prime example of a domain where constraints are used extensively is operations research. We might want to optimize the route for delivery to minimize the travel time, while making sure that constraints on working hours for truck drivers are satisfied. Or we might be scheduling sports matches and want to make sure that matches are not scheduled at the same time in the same stadium and that every team gets enough rest between two matches. Let's look at one example more closely. In nurse scheduling, we're trying to schedule nurses to different shifts, and we want to minimize the cost that we have to pay the nurses for working. Every nurse has an associated cost, which we're trying to minimize, and we have to make sure that every shift has at least one nurse, and each nurse works at most one shift per day. These are the constraints. A possible solution looks like this, where we've assigned a nurse to the morning, afternoon, and night shift, and nurse 2 doesn't work, they have the highest cost. If we represent this solution mathematically, we can represent it as a matrix, where an entry is 1 when a nurse works in a shift and 0 otherwise. Now, of course, real problems are much bigger, with many more nurses and shifts, and finding a solution manually becomes more difficult. This is where we step to constraint modeling. Here, we translate constraints to a formal model in a modeling language such as mixed integer programming. This is what the formulation looks like for the cost, the first constraint, and the second constraint, respectively. Now, after we have translated the model in such a fashion, we can feed this formal model to a solver to obtain a solution. This will also work for much bigger problems, allowing us to tackle these problems without having to manually try to find a solution. In practice, there may be more complicated constraints, and modeling the problem itself is an expensive and time-consuming step, which requires both knowledge of the problem domain, scheduling for nurses in this case, as well as technical knowledge about the modeling language. Constraint learning aims to solve this issue by instead learning a model from data directly. This makes the constraint satisfaction problems and the technological pipeline to solve them more broadly accessible. Ultimately, we want to learn mixed discrete continuous problems with constraints and optimization criteria, for example, mixed integer programs. Such a program in general consists of an objective and a bunch of constraints. And let's focus on learning only the constraints first. Well, in this case, we want to find the feasible region, and we are given a set of possible examples, feasible points. We might also have some negative or infeasible points to learn from. Now, if we also want to find the objective, which for linear programs corresponds to the direction of optimization, we have to change the definition of negative points and positive points. In this setting, a positive example has to be both feasible, that is, it has to fall inside of the feasible area, as well as optimal, while negative examples either violate the constraints or are suboptimal, such as, for example, this point. Existing approaches typically decouple learning the constraints from learning the objective function, learning them in 2 separate steps. For example, first learn the constraints and then the objective, or vice versa. Ultimately, we want to be able to learn them jointly, as the two necessarily depend on each other. Before diving into existing approaches, I want to highlight one more setting that we recently started to explore, learning from contextual examples. Let's reconsider this nurse scheduling example from before. Here we had a schedule which was optimal and feasible, which would be a positive example to learn from. The schedule on the right would be suboptimal, and therefore a negative example. However, given the additional constraint or context that nurse 1 is on leave and thus unavailable, the example becomes optimal or positive in this context. Contexts change the optimal solutions, and that's why it's important that a learning algorithm knows this and can take them into account. It also allows the learner to find models that find not only globally optimal solutions, but find correct solutions when additional constraints are taken into account. Let me illustrate this visually. The context, this yellow line here, imposes additional constraints that change the label of the examples. Examples that were before positive, such as these two, now become infeasible because they don't satisfy the context, while some other examples that were suboptimal before are now optimal solutions, like this one. In general, we can represent contextual examples this way. It's a collection of a point, a context, and a label. And during learning, we're given a set of instances, their label and context, and we try to recover the objective function and the hard constraints. Here we have 3 examples. Examples 1 and 2 have the same context, while example 3 has a different context. We've seen a few of the key concepts that now allow us to categorize constraint learning approaches according to different dimensions. The first dimension to look at is the data. What data do we have available to learn from? We can have positive, negative examples, or we can also have contextual examples. The second dimension is the formalism. What are we trying to learn? It could be SAT or CNF formulas, as well as extensions such as SMT. It could be traditional constraint programs. It could be mixed integer linear programs, which correspond, in the case without objective, to SMT programs. Or we might be learning Excel formulas. The third dimension is the type of problem. Do we have only hard constraints? Do we have soft constraints, such as in MaxSAT? Or do we have a full-blown combinatorial optimization problem? Finally, we can distinguish constraint learning approaches by their solution method. Are they learning by enumeration, solving, or search? We're going to review these concepts a bit more in detail. Let's focus first at only learning constraints and look at a few recent approaches that have tackled this problem. The first approach is to learn by enumeration. The idea is to generate all possible constraints and test whether they hold on the data. Often, approaches try to come up with clever ways to avoid having to enumerate all possible constraints, making it feasible to explore much larger search spaces. This idea goes all the way back to Valiant's original paper on pack learning, where they tackled the problem of learning KCNF formulas from positive examples. And recently, we used an enumeration approach to learn Excel constraints in spreadsheets. The idea is to find constraints such as sums over columns or foreign keys in a set of tables. And the system is given a catalog of constraints to start with. So for here, I'm just going to take 2, sum and foreign key. In practice, there are many more. And it starts by grouping columns into blocks of contiguous blocks that have the same type. Then it generates candidates based on just the properties. So we fill the template placeholders with entire blocks and test whether subsets of these blocks could theoretically make these constraints true based on just the size, type, etc. Finally, the generated candidates are subdivided and the constraints are tested on the actual data. Here, we learn that the data contains both a sum as well as a foreign key constraint, and we obtain the exact positions of the columns involved. The next technique I want to talk about is learning by solving. The idea is to encode a learning problem, learning a model that satisfies all examples, itself as a CSP problem or constraint optimization problem. And then we use an off-the-shelf solver to try to find a solution which encodes a valid model. We use this approach in Int'l to find SMT LRA formulas given a set of positive and negative examples. For those who might not know, SMT LRA is an extension of SAT that allows for linear equalities as atoms. For example, here we have a bunch of linear equalities that occur in this logical formula. The task of an SMT solver is to find a satisfying assignment to both the Boolean and real variables to make this formula true. Now, Int'l poses SMT learning as an SMT problem. The goal is to find CNF formulas with a certain number of clauses and inequalities such that the formula is satisfied by all positive but no negative examples. In this example, we would like to recover the blue feasible area from the positive and negative examples, for example. Using the examples, the SMT learning problem can be encoded as an SMT formula, and the satisfying assignment can be decoded into a valid model. Here you see the encoding that is used, and this is the pipeline that is followed by Int'l. The problem actually corresponds to finding an assignment of Boolean variables and inequalities to clauses, while simultaneously finding the parameters of those inequalities, such as the entire formula encoded by this problem satisfies all the examples. Now, to speed up the learning step, Int'l starts by only encoding a small subset of the examples, finding a model, and then incrementally encoding additional examples that are violated by the current model. We can see this process visually. Here we start off with a bunch of examples. A couple of them are fed to the solver. Int'l learns an initial model. It adds a couple of violating examples, learns an updated model, and continues until it finds a correct model. The key insight is that often only a small subset of examples is necessary to find a model. SMT solvers support incremental solving, and encoding fewer examples leads to smaller problems for the solver, which are then faster to solve. This way we can obtain results that are both fast as well as accurate, so we don't pay really for the speed up. I want to mention a third technique for learning constraints, learning by search. The idea is to start with a very general constraint that covers all or almost all possible assignments and derive more and more specific, that is, restrictive constraints. The algorithm usually stops when constraints become too restrictive, that is, they don't cover a positive example anymore. But in some cases, it might also stop as soon as a sufficient number of negative examples are rejected by the constraints. Today, I will focus on general to specific search, but the opposite approach, specific to general, can also be used in certain cases. Now, we used general to specific search to realize Arnold, an algorithm for learning polynomial integer programming constraints from data. Given a set of examples and some background information in the form of matrices, the goal is to find constraints that hold in the data. For this example, in the nurse scheduling setting we discussed earlier, for all days and shifts, the sum of the number of high and medium skilled nurses must be larger than a threshold, and the skill level of a nurse is encoded in the background knowledge here. Now, Arnold proceeds by starting from a general constraint, and at every step, it makes the constraint more specific, making it more restrictive and including fewer points. The search is defined by a refinement operator, which produces the next candidates in the search space. And here, for example, if we're at this constraint, we can add the additional matrix Mn because it only contains positive values. This makes the constraint H plus M smaller equal to RD more specific, because if this constraint is satisfied, then the previous constraint is definitely also satisfied. We also use a lexicographic ordering to avoid generating the same constraints at different locations in the search tree. This allows us to cut these solutions because they already occur earlier. Applying these methods does not affect the quality of the solutions. However, they realize a significant speed up. Here you can see this is a log scale. So adding these two elements, ordering and general to specific search, really helps obtain solutions much faster. All right, now it's time to talk about learning combinatorial optimization problems, not just constraints. So we're going to start from the contextual examples that we looked at earlier. So we have a point, its context, and a label. And the first setting we looked at, the first simple, non-trivial setting, which was still interesting, is to combine constraints and optimization criteria when learning weighted MaxSAT problems. So weighted MaxSAT is a weighted logical theory, and the goal is to find a feasible assignment with maximal weight. So here we have a hard constraint and two soft constraints with their respective weights. And then given an assignment, we can evaluate if it doesn't satisfy the hard constraint, it becomes infeasible. And otherwise, we can compute its value, and a MaxSAT solver tries to find a solution with maximal value. The Hassel algorithm tries to learn a weighted MaxSAT model from contextual examples. And we studied this problem to learn from a set of contextual input examples. So we have the assignments, we have the labels, and in this example, the context is a partial assignment. So the orange variables here are fixed, and so they are the context with which we work. And we're trying to recover the MaxSAT model. By studying the problem within the PAC learning framework, Kumar et al. Showed that given enough examples and representative context, so context that cover enough of the search space, an approach that minimizes the empirical risk yields accurate results and low regret. And so low regret means that the value of an optimal solution is close to the actual optimum value. Hassel was implemented by encoding the problem approximately as a MILP problem. However, a recent version that uses stochastic local search was able to speed up the learning process and obtain results much faster. Very recently, we have also made some progress towards the goal of learning mixed integer linear programs from data. Now, MILP is the model we're currently working on, and it learns MILP models from contextual examples. We presented this recently at the ICHKA DSO workshop. Given a set of contextual examples where the contexts are additional inequality constraints, the goal is to learn both the objective function as well as the constraints. MILP uses a local search algorithm to obtain iteratively better solutions. It starts from an initial model obtained by taking the convex hull of the positive points. So we know that definitely it covers all the positives. And then it selects a batch of incorrectly classified examples, here these two, and generates neighbors based on the gradient of a surrogate loss. It changes the parameters of the solution slightly based on this loss. Finally, we pick the neighbor with the lowest empirical loss, and then we keep going, either picking a new batch of incorrectly classified examples, or with a small probability, we perform a random restart and go back to an initial model. Now, the goal of constraint learning is to make constraint-based models and solvers more broadly accessible. Of course, this means that using these constraint learners itself should also be accessible. We have worked on a constraint learning framework that connects through Excel through a plugin and makes it easy to learn constraints and solve problems right from within a spreadsheet. Here, for example, the user loads some tables, including two schedules, and then pushes a button to learn constraints. Here we have 3 different constraint learners implemented. You just push the button and the framework will pass the data to the constraint learners, return the learned schedules. So here we have a bunch of scheduling rules. And Tackle also was able to find a conditional sum constraint. All of these constraints together are translated to a common constraint language. In this case, that's MILP. And the user can then autocomplete any missing value. So this completion step uses a solver. We're using Gurobi behind the scenes. And we find a model that fulfills all the constraints and predicts all of these values in green that were previously missing. All right, before ending today, I quickly want to point out a few important areas of related work. In the last few years, we have seen a lot of work on learning constraints. First for the discrete case with systems such as Model Seeker and CONAC, then for linear constraints, and recently for mixed discrete continuous models. Most of the focus so far has been on learning hard constraints and less on learning constraints and objective functions jointly. In parallel, there's been a lot of work on inverse optimization, which broadly we could say focuses more on learning an objective function, where the goal is to modify a given model according to a set of examples. Finally, decision-focused learning predicts part of a model based on other features, and it uses a predictive machine learning algorithm for this. And then it tries to couple feedback on how well that learned formal model is performing back to the predictive algorithm. We see a lot of potential for future work in several key directions. Aside from faster and more expressive learners, we believe an important different angle is to integrate additional background knowledge from the user. For example, through the use of sketching, where we can use a partial model, parts of a constraint. So here, for example, we know that we should constrain the sum of the shifts, but we don't know how. Or we might have some known parameters, such as a cost factor. Now we want to integrate this background knowledge during learning to speed it up and to use all the available knowledge. I also want to briefly mention learning of tractable models. As we learn more and more expressive models, they actually become harder to solve. And that's when it starts to make sense to already take the solver into account during the learning phase and produce models which will be easier to solve in the end. I want to point out a key challenge, which I think is interesting to have a look at as a field collectively, and this relates to the fields of active learning and preference elicitation. Here, the goal is to uncover user preferences in the form of an objective function. And many constrained learners nowadays use positive or negative examples to learn from, but in many settings, it might be much more informative to ask smart queries or use preferences. So for example, here, we might have two examples and the user indicates which one is better, but we might also have an interactive system where the machine proposes a solution and the user then corrects or makes a small tweak to the solution that makes it better. For discrete problems, systems such as Quack or CONAC already explored the connection between active learning and constrained learning, but I think it also makes sense to investigate these connections for mixed models and constraint optimization models, where so far we don't have many results. Thank you very much for attending our talk today, and we'll be available for questions.